And that's Margaret. So just missing Eliezer. Right, so we are going to today learn about, come on, times and seasons. There we go. Why do you suppose that the theme for actually Unit 6 in the textbook is Stonehenge? Go ahead. Sarah, right?
Sarah.
Oh.
Sarah.
Meg. Yeah, okay.
With me?
Yeah, you used the one I... Meg.
Because it was actually a lunar calendar, wasn't it?
We believe that that's... Now, there are lots of different theories about how it was used. But one thing that is incontrovertible is that it is lined up so that on the winter solstice, which is, well, where we essentially start the year, that they had things aligned so you'd have a special alignment there. And so it is conjectured that there was a calendar-ish aspect to it, as well as, probably sacrifices and other things that are not so wholesome and fun as a calendar. So we're going to learn about how the calendar relates to astronomy. And I'm actually going to start with something that I just found humorous. I saw this just before I taught this lecture last year. Richard Branson posted a picture of the sunrise as viewed from Mars, a picture that NASA took. And this comment here, I never knew Mars had a sun. Yeah, pretty genius. Just in case people don't remember, which I'm sure you all do, the sun is the absolutely nearest star, and we orbit it, and so does Mars. And this is a better picture. I believe that's an accurate picture taken by a rover showing not just stars and planets. Rigel is a planet. That is, or not a planet, is a star. Rigel is a blue giant.
Is it Rigel or Eagle?
I have learned to call it Rigel. I learned that from the TV show Farscape. They wouldn't steer me wrong. Much like, you guys probably haven't even seen Back to the Future. But, oh, you have? Okay, so 1.21 gigawatts. No one on the set knew how to pronounce giga. They've actually talked about that. No one knew, so they just tried to guess, and they guessed giga. And so now you can find places where people write gigawatts, J-I-G-A. It's funny. Okay, so that's a star. Since I don't know this one, I assume it's also a star because I'm pretty sure I know the planets. Venus and Earth, they are planets. Deimos and Phobos, those are the moons of Mars. Phobos is fear, Deimos is terror. They actually are basically asteroids that got captured. They're not like our moon at all. Okay, so that was just kind of a fun thing there. The celestial sphere. I truly believe that when we watch the Simpsons episode, you will have this as a quotation you hear. Since the earliest times, humans have sought to understand the night sky. Actually, it's humans have been something like enthralled by the night sky. It's pretty close, though. I think it stands to reason to make this assumption. We can't say, what was going on in Adam and Eve's time, but we do know that from recorded history, there's a lot of things about astronomy. If you read in the Bible, you have in Genesis talking about how God, made the greater light to rule the day and the lesser light to rule the night. And we have things like David talking about God creating the stars and everything. That's just about as old as recorded history goes. And so it's a good assumption since the earliest time, certainly from the earliest recorded history, we have evidence of people trying to understand the night sky and looking at it as something majestic and cool. And a useful model of the sky is called the celestial sphere. Now, once again, this model was believed by Aristotle to be factual. Aristotle thought that there was a sphere out there that all the stars were on. So you see in this picture, out here is supposed to be showing where the actual stars are. And the model says that we have a crystal sphere here, because Aristotle said crystal is the perfect material and it's all perfect out there, so it must be a crystal sphere. And then you have the stars located just on that sphere. So Aristotle's idea, the celestial sphere, says all of the stars are just on this sphere. The reality is not. The reality is the stars are varying distances away, some very far, some not so far. But it looked that way, and so that was Aristotle's belief, and we still use that as a model to make it so we can understand star locations. So now recall, a model is basically an analogy. A model says it's like this, not it is this. And so to help us identify where stars are located, we'll learn by the end of today exactly how they do that. We use this model of a celestial sphere. So the stars are located, well, I just said various distances, but they appear to be there. And the stars appear to move. And of course, up until the time of, let's say, well, up until the time of the demise of Copernicus, people believed that the Earth was stationary and that all of the stars were rotating around the Earth. So that celestial sphere would do one rotation a day. Now, if those stars are very far out there, it doesn't take a genius to realize they must be moving super quick if they're doing an entire lap around us in a day. But they didn't really have the concept of how far and how fast that would have to be, and that was the belief until fairly recently. So the motion that you see of the stars across the sky is the daily motion. Now, this is coming up in the coming slides, but riddle me this. Where does the sun rise? It rises in the east. Where is it set?
West.
The west. We can read that in the Bible, right? It's been the same from the Bible times to now. If you have ever watched, how many people have ever seen the TV show Street Smarts? Really? Usually that answer is nobody. It's one of those lame game shows, and of course, my siblings and I like these lame game shows. And what they do in Street Smarts is they try to find idiots on the street. And then they ask them a number of simple questions, and the contestants in the game show, their job is to guess things like, how many people out of 3 got this question right? Or then later on, which one of these 3 do you think got it right? And so the question was, how many people got this question right? And I posed it the way they did. In the northern hemisphere, the sun rises in the east and sets in the west. In the southern hemisphere, where does the sun rise? It's going to be the same. It still rises in the east and sets in the west. And it was only 1 out of those 3 people who realized, yeah, and they never said it's in the, like the Bible doesn't say, in the north the sun rises in the east. It's the sun rises in the east. What about the stars? Where does Rigel rise? It's going to be the same in the east. Rigel rises for the same reason that the sun rises. The stars are out there and we're rotating. And as we rotate, actually, okay, we're rotating this way. We rotate toward them until, hey, they appear over the eastern horizon. Then we keep rotating until they're overhead. Then we keep going and they set in the west horizon. So the stars rise and set just like the sun does. Every day, the sun rises and sets. Every day, the stars rise and set. Every day, the planets rise and set. Because the earth is rotating. Even the moon.
It was Aristotle, you said, who had the sphere.
Yeah, we will actually go through the history more carefully later. So we'll cover Aristotle's model actually coming up soon. Now, some important terms that we use in conjunction with the celestial sphere. We have things like the word zenith. Zenith. Television brands, for all I know. Zenith is a word that means directly overhead. So if you stand up straight, whatever is pointing above your head is your zenith. Now, I had students last night in the first group note that Lyra was at their zenith when we started. I didn't say the word zenith. Did you guys think to look at where it was when we left? Or Vega, actually, where I started. It had moved over to about there. I did check, but I didn't say, hey, you guys, check, because, well, in my mind, out of my mind. So zenith means the point directly over your head. Now, the opposite of the zenith is the nadir. The nadir is directly underfoot. So if you were to go through your feet, through the earth, out the other side of the earth, that's where your nadir is. So it's your zenith, your nadir. You move around, you change where your zenith is, you change where your nadir is. But those are things we use for locating where we are. Then we have the celestial pole. The earth rotates on an axis. And that axis, we say, has the North Pole and the South Pole, the two places where the axis would go into and out of the earth if we actually had a pole that the earth was spinning on. And the celestial North and South poles are simply you take a line that goes from the center of the earth out through the North Pole and you extend it until you hit that imaginary celestial sphere, and that's the celestial North Pole. And likewise, you take a line that comes out of the South Pole and goes down until it hits that celestial sphere, and that's the celestial South Pole. So,
that's the celestial?
Celestial, yeah. So the North Pole is on the earth. The celestial North Pole is just directly above the North Pole. The South Pole is on the earth. Celestial is directly, well, we would say below because we're up in the northern hemisphere, the South Pole. And we have the celestial equator. The earth has an equator. That is, we are rotating about that axis, the poles, and we have the equator that is the center point between the poles. The equator makes a line around the earth, and if you were to take that line and just extend it outward until you hit the celestial sphere, that defines the celestial equator. So on the celestial sphere, we have the equivalence of the poles and the equator, just like they are on Earth, just extending them out. Why do we do this? To give us easy points of reference. Horizon is a little more tricky of a word. Well, not really. It's just you don't think about it. Horizon has as its root horizontal. And so the horizon, I should have grouped it with the top two words. The horizon is horizontal from wherever you are. So my horizon goes like this. My parents out in California, their horizon is going to be different because they're standing at a different location on the earth. But the horizon is going out horizontal from your position. I don't think I have them in here. I want to do a few more vocab words. Yeah, you didn't see that question. A few more vocab words before we go to the first clicker question. I've talked about our zenith, the point directly over our head. There's another term that's kind of important, and that is your meridian. Your meridian is the line that goes from the south celestial pole up through your zenith to the north celestial pole. Now, why is that important? Well, AM and PM. Everybody knows AM and PM, right? Put them together and you have a meaning marking. AM, actually, a lot of people don't know literally what AM is. Do you know what the words are that A and M stand for?
It's meridian and non-meridian, right?
AM is anti-meridian, and PM is post-meridian, much simpler. Anti is before, post is after. So AM very literally means the sun has not yet reached your meridian. So for each location, your meridian is the line that goes from the south celestial, south, north, that's north, south. So from the north celestial pole up through my zenith to my south celestial pole. If it's in the AM, the anti-meridian, that means the sun is over here on the east and has not reached that line that goes over my head yet. And if it's post-meridian, it's past there. And what do you call it if the sun is on your meridian? Midday, or more commonly noon. Noon is supposed to be when the sun is at your meridian. So if somebody talks about local noon, they should be saying the time when the sun is on your meridian. Not necessarily overhead, because up here, about 40 degrees north of the equator, the sun never passes overhead. But when it's on our meridian, that's the local noon. Local noon does not always correspond to what it says on a clock. The time for noon moves back and forth in a controlled and calculable fashion, of course. And so our watches, when it says noon on our watch, it doesn't actually correspond to what it's supposed to be. And something that I'm a really stupid stickler for, my little sister, she's a physician, she thinks I'm an idiot for caring about this, is 12 noon a.m. or p.m.?
12 noon
Yeah.
is going to be PM.
It's neither. It's 12 noon, period.
I thought you were asking like on the clock.
Yeah. Well, on the clock, yeah. On the clock, 12 noon is neither a.m. nor p.m. And I don't know that I've ever seen an official abbreviation for it, but it bedevils me when somebody says, this is due at 12 p.m. Because I'm very literal, and I'm like, there is no 12 p.m. I have no idea if this is due at 12 noon or 12 p.m. I have lots of my assignments that are due at 12 p.m. 12 p.m. 12 midnight. Yeah, I just said it, yeah. I have lots of assignments that are due at 12 midnight. But, is it a.m. or p.m.? It's neither. Okay, so the reason I'm a stickler on this is for the very literal meaning of the words. A.m. is before noon, p.m. is afternoon. Neither one fits into at noon. Okay, so meridian is a semi-important word for us to understand things like how the day is divided. Now, into which category does the oh, come on, move forward. Don't answer yet. Now answer. I didn't get this set. Into which category does the celestial sphere fall?
They didn't have one at the campus store. I tried to get one this morning and they're out.
So the one that's registered for you, you no longer have?
I tried to find it.
What's the channel?
Channel 33. I don't know, it's supposed to be posted somewhere. There's also a little thing here that helps you none. It says Channel 33. I thought you were all good because you had one registered. Alina said that you couldn't buy one, and I was like, but she already has one.
Yeah.
It's not letting me change the channel on mine, but it could also be because I don't remember to use these.
Well, Cody knows how.
I'll have to change channel
I'm actually going to make sure that he gets this done just as,
Yeah, I mean, like I found the change channel thing, but it goes to this.
Okay.
So, yes, need presentation. Yeah. Oh, you're enter.
Blog.
I was
My
thinking
roommate
you
doesn't
said
do that.
There you go.
But now what?
You just need to press the button. Oh, there are some where you do have to press enter when there's multiple answers, but otherwise just press the button. It should say this recording. Okay. Only 10 people? Well, actually, there's only 13 people in the class, it turns out, so that's... We know you two didn't answer.
I didn't answer either.
Okay, so there we have it. All right, and we had people at the last minute change their answers to the correct answer. Good job. Nine out of 10 respondents said that the celestial sphere is a model. What makes the celestial sphere a model rather than any of these others?
All their theories hasn't been tested to be true.
Okay, it's not a theory it hasn't been tested multiple times to try to disprove it. In fact, we know it's not true. So it couldn't be a theory. We know it's not true. Theories we believe are true.
Can't be a fact either if it's
That's right. It can't be a fact if it's not true.
not. Or a law.
A law. Laws are things that have usually just a simple equation that cover a broad range of circumstances. Principles are more narrow. That's not a word we had. So, yep, model it is. Basically an analogy, something to help us understand. Now here's some pretty pictures. Can anybody tell me what's in this top picture?
Looks like a horse.
Okay, stars was obviously correct, but
I didn't get to a constellation.
An asterism.
constellation.
It's actually plasma.
Is the constellation Leo the lion?
Yes, it is. When I look at this, I see a question mark or a coat hanger. I see that I have to change colors. That's the first thing I see. When I see that, I say, oh, that's Leo. The rest of him
The hunter, right?
is going to be, no, the lion.
No.
The rest of him is going like, yeah. I don't know why you have this part. Let me not put that there. That's ridiculous. That's got to be his tail, right?
I thought it looked like a horse.
You can believe that looks like a horse. That's fine. I mean, we're talking pretty random, right?
It's art.
Yes, it's art.
Abstract.
And this is my art. So that's supposed to be Leo. Now let's look at the picture the book gave us. There's the picture the book gave us. Wasn't that pretty cool, huh? I was going to go like this to erase.
Oh, now I see it.
Okay, enough having fun.
The bottom was a sword, right?
Okay, the bottom one has the asterism that Eliezer likes to call the sword. We pointed this out last night. Now, it was pretty light last night. We couldn't see nearly the detail here. Anyone have an idea what all of this white is around here? That's the Milky Way galaxy. That's the collective light from billions of stars. And there's so many stars way out there that the light just looks like a cloud. And so we talked last night about first the asterism that Eliezer calls the sword.
That's really a swan.
Well, the asterism we usually call Northern Cross or something like that. That's the asterism. If we want to talk about the constellation, we have wings that are coming out here. Can't see all the stars to continue on. And so the constellation is clearly much bigger than what we're seeing here. Now, once again, we got a picture here. Actually, let's do it the fun way. Isn't that fun? Okay. I am now officially bored. So there's the textbook's picture they gave us for the swan, of Cygnus the swan. So you can see the pictogram idea for the constellation here. Now, I went one step further. What did I tell you a constellation really is? It's an area. Now, that is a modern definition for constellation. Things have evolved over time from just the pictogram to saying we're going to use these constellations like we would a continent or a country. So think of the constellations kind of like countries. There are 88 countries on the celestial sphere. And all of the entire sphere is filled up by these countries. There's no gaps. There's no open spaces. So to make that work, over here you can see the actual shape of Leo. Let me zoom in a little just to see that more clearly. So the shape of the constellation is the white area here. Now, I am not going to expect you to have that perfectly, okay, so you come, you do a jog, and then another one, and then you come up for the lab final. Instead, what I'm going to be looking for is something like that, right? Something that's a rough shape for it. But not something like, here's a wrong answer for Leo. right? You got to realize, okay, it comes down here for the hind leg, things like that. So that's what Leo looks like. So if you come out here and you try to match it up, this here is this here, so it comes down here. This here is that, so it's going to go. Something. You know, it's shaped something like that. That's my best rendition of it. And you can kind of see the blue. I forgot that I changed to a bad color. Okay, so Cygnus. Here's what the constellation Cygnus looks like. Now, you'll probably recognize I was sloppy last night, wasn't I? Because when I pointed out Cygnus last night, I basically did like that. Now, it's fine on this side, but I really should have come out like that. Squared it off. Square it off from the wing to the wing instead of this here. Now, that still didn't follow this exactly, but you don't have to be exact that way, just be roughly correct. And so you can see here the swan, the wings come out, additional stars out. This wing comes all the way out. Well, okay, the summer triangle, we have Deneb right here. We have Vega right there. And then it's off the screen, but somewhere around, I think it's around here, is where we have the one that again escapes my mind. What was it? Yeah, Altair. You get mental blocks, life goes to pot. Keep in mind there's no pot involved in my mind. So, with constellations, how many were there? I tried to cover it up. How many constellations are there? Yeah, there are 88 internationally recognized constellations. Most of the nice pictogram constellations are in the northern hemisphere. I mentioned this briefly last night. Why would it be that most of the nice pictogram constellations are in the northern hemisphere? Yeah, that's where 90% of the world lives. And so most of the people who've been identifying constellations live up in the northern hemisphere. There are lots of constellations, and then they just move the boundaries around to fill space. But then you got the southern hemisphere that doesn't have much that was predefined. And they're all like, well, we got to fill this up, so what do we do? Well, if you look, you've got a star there, and a star there, and a star there. You put that together, and that makes a triangle. So we have a constellation named Triangulum. There's another one. This guy's my witness. I have no idea how they got it, but it's like Microscopium. Somehow they imagined they saw a microscope up there. So we have a few constellations in the southern hemisphere that you kind of shake your head at. But we have a total of 88 covering the entire sky. Any star that is within the boundary of a constellation is part of that constellation. And every star can only be in one constellation. It actually brings up an interesting thing. You guys had the Great Square Pegasus pointed out last night by Reese. And Alpheratz, the star we usually start at for that Great Square, used to be part of both Andromeda and Pegasus. It was part of the body of Pegasus, and it was an eye for Andromeda. And so when they said, okay, we're going to put delineations and stars can only be part of one constellation, they had to draw the constellation boundaries so that it would be in one or the other. And the choice was to put it in Andromeda. So that Great Square Pegasus, Alpheratz at the corner, is in Andromeda. It's just barely outside of Pegasus because they just had to draw boundaries so it would only be in one. The constellation names. What language are those constellation names in? They're in Latin. They may have other origins, but they're in Latin, so you have the Latin conjugation, so you have like Scorpius and Taurus and, Microscopium, Triangulum. So the constellations are all in Latin. Star names. What language do star names tend to be in?
I venture to say Greek.
I'm going to venture to say star names, the predominant star names are things like Alcor, Al-Qaeda, no Al-Qaeda, Aldebaran. What does Al, where do you hear Al in names? Arabic. Many of the star names are in Arabic. And the reason for that is very simple history. Where was the center of science and knowledge? The center of science and knowledge moved from Greeks through the Arab world, and actually I can't remember the exact sequence of where it went, but the Arabs were the dominant scholars in the world at one point in time, and they had their names for the stars, and the rest of the world adopted them because those were the dominant scientific, authorities. And so we have a lot of Arabic names for the stars. Stars actually have multiple names. Things like, Alpha Centauri. You've heard of Alpha Centauri, right? Alpha Centauri. Alpha, this is the Bayer naming convention. Alpha is used for the brightest star in the constellation. So Alpha Centauri means that it is, the Centauri is, I guess, the possessive form of Centaurus. And so Alpha Centauri means it's the brightest star that belongs to Centaurus. And Beta Centauri would be the second brightest, and so on. And so you have a naming method. You can't use those names for named stars if there is a common name, right? You can't just say, that must be the brightest star in the constellation Cygnus, so I'm going to call it Alpha Cygni, and you'd better give me credit, right? But that would be true. You would have that name for the brightest star in Cygnus. Okay, some popular patterns are not in constellations, they're asterisms. The first day of class, I had a question. What's an asterism? Last night in lab, we pointed out some asterisms. And some of the very common, well-known asterisms are the Big Dipper, which is part of Ursa Major, the Teapot, part of Sagittarius. What are some other asterisms that you guys can name right offhand?
Orion's Belt.
Okay, I heard Orion's Belt. What'd you say?
The Northern Cross. The Summer Triangle.
And yes, when you do the lab final, I'm just going to draw a triangle for the summer triangle, right? You say it right, and I just draw. I can't read what I write anyway until afterward. I go turn on the lights and see what I wrote. Anybody got any more?
There's that one, she's like a queen, or something.
That's the pictogram that goes with the constellation itself. So that's Cassiopeia. It doesn't count as an asterism because it's the one that goes with the constellation. Well, let's see.
Orion's Dagger.
Okay, Orion's Dagger. Or sword, depends on who you talk to. I call it a dagger, some people call it a sword.
I always thought it was his belt.
Well,
Part
no,
of his belt that
they're
was
different.
taken down.
Oh, it's the belt tag, you know. It's the style these days.
Like the cholo, like the fabric belt that comes down.
Doesn't the lion have a dog and wouldn't like the leash or the dog be some
Well, Canis Majoris and Canis Minoris are both constellations that are trailing behind Orion. They're two of his hunting dogs. There are a couple other Canis out there, but they're their own constellations.
okay.
Canis Majoris is the one that has Sirius, the dog star, in it. I read the textbook in preparation for today and saw something that I had not seen before. The dog days of summer. Did you guys read the textbook and see what the origin of the dog days of summer is? According to our textbook, and why would they lie? The Egyptians would look for the rising of Sirius, the dog star, on the horizon at sunset, and when it rose, that meant that it was time to plant the crops or something like that. Or no, it was time to prepare for flooding of the Nile River, I think it was. And so looking for the dog star set off the dog days, the days when you had the dog star in the evening sky and you were prone to have flooding of the Nile River. And we still call them the dog days of summer today. Yeah, that's what the textbook said. I believe him. I've never looked that up before. I've never seen it before. But there's a lot of fun things in astronomy. Have I mentioned why we have 360 degrees in a circle? No? Well, go ahead.
60 days in a year.
That's right. There are roughly 360 days in a year. And, these ancient astronomers figured out that you have a repeating cycle with the stars. And so they designated the year for the time for the repeating cycle of the stars. And, we know the number today to be 365.2422 days in a year. Yeah, my wife just realized she forgot my lunch. I realized over an hour and a half ago. She said, "I'll bring you lunch today. I'll come at 12:30.
She never showed up.
She never showed up. I'm withering before your eyes. Enough on that. Okay, so 365 days roughly in a year. And they said, 365, sure, that's a fine number. But 360 is so beautiful. Because 360 is evenly divisible by 1, 2, 3, 4, 5, 6. Got to skip 7. 8, 9, 10. Got to skip 11. And 12. All but 2 of the first 12 numbers. And they said there must be something magical about a number that's so divisible by everything. And it's certainly going to make our math easier. You've probably seen some of those goofy things about angles and circles and the magic therein. They chose 360 degrees because it was a cool number and had these properties. And so basically a degree is to represent the amount that the sun moves in the sky each day. And it's just off by a little. Instead of 365 degrees in a circle, they put 360 because it was a more cool number. So what that means is if you were to go out and look at the position of the sun with respect to the stars, which of course you can't really do that because when the sun's out you can't see the stars. But if you were to do that every day, you would see that the distance the sun moves against the stars is roughly 1 degree every day. That's where it comes from. So with our celestial sphere, we can put angles going around. And we do put angles going north to south. The angles going north to south are called, here it has lines of ascension and lines of declination written. The declination is the angle north or south of the equator. And that's on Earth, we would call that the latitude for the angle north to south of the equator. On the celestial sphere, it's the declination. So, and I know I have these coming up probably in the next slide, but I'm going to write them down anyway, the declination is equivalent to latitude. Latitude. And so they measure that in angles, just like you'd expect. Going around this way, look at what they have. You see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. They're not going to get up to 360 with that. The equivalent to longitude is called right ascension. And it's measured in hours, minutes, and seconds. The reason for that is simple. You measure the angle along the equator in hours, minutes, and seconds on the celestial sphere. And if I go out and what's at my zenith is at 12 hours right ascension, if I wait 1 hour, the star of my zenith is going to be 1 hour higher than 12, 13 hours right ascension. So you can use a clock to time the motion of the stars with the right ascension. That's why it uses that. Now I'm going to get to some interesting ideas that relate to that. But first, when stars set, if you're standing here in the northern hemisphere, you see stars set on the west, hence we see the west there, but they don't set straight down. They're going in a northwest direction. Why are they going north?
They're not.
Well, as viewed from the earth, they're going north. Why do they appear to be going north? Right, I mean, the fact is we're rotating, they're not moving, right?
Well, they're moving too, but
They're moving too, but we can't see that motion. Because we're rotating and those are coming around, if you're in the northern hemisphere, the stars are going to move north as they set because of the rotation. And as they rise, they're going to come up and start going south. So when the sun rises, sometimes the sun will rise north of the equator, sometimes it will rise south of the equator. But it will always pass south of us because, well, we're 20 degrees north. And I really need to get forward to that slide that talks about it before I go further on it. So here is talking about locations on Earth. We measure longitudes as angles from the prime meridian. In the sky, we measure, instead of longitude, what did I say we used? Right ascension. We measure the right ascensions, and we measure those from a line called the equinoctial color, which is why you're learning it for part of your lab final. That's where we measure the right ascensions from. The latitude on Earth, we measure it from the equator. Where would we measure? Well, what do we call the equivalent to latitude for astronomy? It's the declination. And we measure it from the celestial equator. So the declination, pretty much exactly like latitude, just measured on the celestial sphere. Longitude and right ascension, the difference is the units. We use degrees for longitude. We use hours, minutes, seconds for the right ascension. And right ascension is going to appear on this slide, and declination. But I've already talked about those, so we don't need to. This is just a picture to show that for mapping stars, we map them out with the right ascension and declination on a grid. Just like if you looked at a map of the Earth, we would have latitude and longitude on a grid. And just like on Earth, we tried to take a curved surface, right? The celestial sphere would have been a curved surface. And we tried to flatten it out, and so you end up with lines that bend and curve so that this is a shorter distance here than it is here, because we're trying to take a flat surface or a curved surface and put it on flat paper. I laugh and laugh and laugh when people take a map and say they've been lying to you because the maps are trying to flatten out the globe, and they translate that as trying to make countries that are farther away from the equator appear more important on the maps by making them look larger. Not trying to make them look larger, just trying to flatten out the map. When we measure positions in the sky, angles is really the only thing we can use for measuring. So when you measure the distance from, let's say, one constellation to another, you measure the angle between them. And so this has some quick guides to help you judge angles. So the width of a pinky is supposed to be about 1 degree. Obviously, it depends on your pinky. My pinky is probably bigger than your pinky. But if I hold it out at arm's length, the angle is probably pretty similar because the size of my pinky and the length of my arm both scale. So if I hold it out farther and it's bigger, it can be the same angle. So the pinky about 1 degree, the thumb about 2 degrees. That presupposes your thumb is about twice as wide as your pinky. And your span, if you hold it out from pinky to thumb, about 20 degrees. I think we all know that is more flexible from one person to another. So just things to help you judge angles. And here is a good one that you can check. The angle between the first star in the handle of the Big Dipper and the bottom of the cup of the Big Dipper is approximately 20 degrees. So you can go out there, hold your hand, span out, and say, for me, is that 20 degrees or is it more or less? Because you know what 20 degrees is if you use that as a reference point. So next time we go out, I'll try to remember to have people do the hand span thing and compare the angles. I only have 4 minutes left. So, it's a pity. You ever seen a cool picture like this?
No, no.
How do they make that?
Long exposure.
Okay, long exposure. You set up a camera and a tripod at night, and you let it run for long exposure. Why do you have these? I mean, I look up at the sky and I never see those.
Really?
It's true.
So once I'm moving and it's producing like every second.
Okay, now, what she said fits in with the ancient belief or with the model of the celestial sphere, that celestial sphere is rotating around us. Right. There's nothing wrong because we think about it that way. I mean, I teach you about the celestial sphere. You know, how am I going to then say, no, you can't think about it that way? So we think about it as if the celestial sphere is rotating around us. In fact, what's happening is we're rotating within. And so things that are up here at the celestial North Pole, because we're in the northern hemisphere, we can see the celestial North Pole, appear stationary, and then the other stars are going around that point as the Earth rotates. So that's how these are made, and they're very cool. You forget all the stars appear to move as we watch them. The analemma. You might see that, not in our textbook. These are pictures. I was reading about the analemma in preparation for today's lecture, and the person was saying, now, if you ever see a vertical analemma, you know that it's photoshopped. You never get a vertical analemma. It can only be vertical like at the North or South Pole, but at the North or South Pole, you don't have a complete analemma. Well, the one that I had, which came from an earlier version of this textbook, was vertical. I was like, oh, crud. I never even paid attention to that. So I got this one from NASA's astronomy picture of the day, thinking, oh, that should be good. And then I read the fine print. We superimposed an analemma on the Apollos, or whatever it is, and we set the angle so it would be correct for that location. In other words, this one here is also photoshopped. It's not. This is a real photograph of an analemma, but then it's been rotated and superimposed to match what you should have gotten if somebody had actually set up a camera there to take the pictures. The way they make this analemma is you just set your camera to, in this case, probably about every 10 days, snap a photograph at the same exact time. So at 9 a.m., let's say, that's what this was taken at 9 a.m. At 9 a.m. every day, the camera snaps a picture on the same film. And so you see how the sun is at different locations at 9 a.m. every day. And when the sun is down here at the bottom, that's going to be the lowest the sun ever is, which we call the winter solstice. At the top here, that's when the sun was at its highest point it ever gets, which is the summer solstice. And in the middle, which I think is these two here, is at the equinox. What's happening in this picture is we're seeing that the actual time when the sun is overhead shifts with the seasons. So noon is not 24 hours away every time. It's shifting. We approximate and we use an average solar day. The mean solar day is 24 hours long. But the solar day is different every day of the year, right? It gets longer and gets shorter. It actually is longer from noon to noon sometimes than it is other times. And that's indicated by the shifting of this left and right. So that's what the analemma is all about. And let's see, is this a good stopping? Yeah, this is a good stopping point. We'll start with the zodiac next class period.
Yay, Zodiac Killer. No.
You know the Zodiac Killer attacked and killed some PUC students, right?
Some UC students, really?
PUC, Pacific